Hello again, welcome back. Next, we're gonna finish up chapter one. Chapter one has a little bit of everything, review of some general chemistry topics, and a first look at organic molecules and their 3D shapes, how can we draw them and so on. We're kind of laying the foundations here that are needed for the rest of the chapters. In fact, you're gonna find that for these early chapters, really all of Chem 3140 is laying the foundation for 3150, but these first 6 chapters are giving us all the tools we need to finally start studying organic reactions and their mechanisms and predicting the products of reactions and so on. So I know chapter one's a little bit all over the place. The later chapters are really going to be more centered around a single theme, so that'll be a little easier to get used to. So okay, let's take a look at our lecture notes. We are on page 8 of our skeleton notes. If I can find that, there they are. So we just finished up drawing 3-dimensional sketches based on hybridization. And now we're going to look at the last topic in chapter 1, and that is physical properties. There's some really cool interactive simulations at this website. And so hopefully in our problem solving session, we can take a look at some of those and work through those. They're pretty cool. Because a lot of this has, if you could have some visuals tied in with the phenomenon, I think that can help make sense of things. So there's 2 physical properties that we're going to be looking at, and that is boiling points and water solubility, and we'll explore some examples of both of those. So both of those physical properties can be described or can be predicted based on intermolecular forces or attraction. So when you say intermolecular, what that means is between molecules. So what kind of attractions do we have that hold molecules close to each other? So let's think about this. What do you think this picture is showing here? We have these little molecules of CH3OH, that's methanol. We have all these methanol molecules that are very close to each other. They're touching each other. As we heat this mixture, we add heat, it increases kinetic energy until eventually these molecules are separate from each other. So what do you think these 2 drawings are representing? This first drawing is representing methanol in its liquid form. Methanol as a liquid where all the molecules are touching each other. There's a lot of motion between them, but they have a lot of contact as well. But when you heat it and you reach the temperature described as the boiling point for that substance, you end up converting that liquid into a gaseous form where it's still methanol molecules. Notice the molecule is still complete and intact. They're just no longer touching each other. So we have to tear those molecules apart from each other to put them in the gaseous phase, right? So what we're not looking at, these are not carbons and hydrogens and oxygens all floating around, right? Absolutely not. We are not splitting apart the molecule. We're simply separating one molecule from another. Okay, now, if these methanol molecules are very strongly attracted to one another, then what effect does that have? That means it's going to require a lot of energy to separate one from the other. And what is that going to do to the boiling point? If it's going to be difficult to separate one from the other, that means the boiling point is going to be higher than we would expect otherwise. I don't want to cover up the word, sorry. It's going to be a high boiling point if there's a very strong attraction between molecules. So let's think about what kind of interactions can we have between molecules. We describe these as non-bonding interactions because there aren't bonds connecting the molecules, but there are attractions nonetheless. So there's 3 main effects that we're going to be looking at. One is called dipole-dipole, and that's what we have for polar molecules. So once we determine that a molecule is polar, then that's the attraction they can have with each other, is called dipole-dipole. We can also have hydrogen bonding, which is a very strong attraction that we have when there are OH or NH groups on a molecule. If you have an OH or an NH, we can have a special attraction described as hydrogen bonding. And then finally, we can have van der Waals, or which sometimes I just abbreviate VDW, van der Waals, or London dispersion forces. And these are found in all compounds. All compounds exhibit van der Waals or London forces, but it's but for nonpolar compounds, this is the only force, the only attractive force. Okay, so it's very common to say, oh, London forces, that's what nonpolar compounds have. But I don't want you to mistakenly think that only nonpolar compounds have London forces. All molecules have London forces, but some have, on top of that, they have dipole, and they have hydrogen bonding as well. All right, so let's look at these one by one and see what effects that they can have. So when we say that we have a polar molecule, remember we talked about having certain covalent bonds can be polar covalent bonds, which means that one part of the molecule, I shouldn't really have a minus and a plus. I should really have a partial minus and a partial plus. Remember, we use that delta sign to represent a partial. So that means the electrons are not evenly distributed in the molecule. They're kind of there's a higher region of electron density in one area than the other. So just like a magnet has two poles, we could think of a polar molecule as having two poles, right? A partial plus end and a partial minus end. And so you might imagine, just like a magnet, when you bring this together with another polar molecule, you're going to expect that they stick together pretty well. So the opposites attract. The partial positive end is going to be attracted to the partial minus end of the other, and so on, etc. Okay, so like magnets, they're going to stick together pretty well. So let's take a look at some sample data here. Let's look at these two compounds and compare their boiling points. I'm giving you their boiling points. This says 76 degrees. This says 36 degrees. They're roughly the same size molecules, and that's that's important to keep in mind, because we want to we don't want to compare apples to oranges. So these molecules are roughly the same size, but are they both polar? Or is either one of them polar, or are they both polar? Do we have any polar bonds? Yeah, here's where we have a polar bond in the direction of the oxygen. And so this molecule is a polar molecule, while this hydrocarbon here is a non-polar molecule. Remember, carbon-carbon bonds are nonpolar, carbon-hydrogen bonds are nonpolar. So there's nothing about this molecule that would have any polarity, would have any permanent dipole moment. And that's what explains the boiling point trend. The overall trend is that as you increase your polarity, you increase your boiling point. So we would expect this molecule with the CO double bond to have a much stronger attraction between molecules, so it takes a lot more energy to separate them and put them into the boiling phase. Okay, now what do we have over here? Look at that boiling point, 1,400 degrees. That's pretty crazy. So what's going on here? Well, this is not just a polar molecule, right? This is sodium plus and chloride minus NaCl. This is ionic. These attractions are ion attractions. So that's not really in the same category. Again, just showing the total extreme of having actual ionic charges. That's the strongest attraction you can have, is between those ions, and those are so strongly attracted that there's no way you're separating them. In fact, even trying to melt them is going to be very, very hard. Have you ever if you fry some eggs and then you maybe salt the eggs while they're still in the pan? Have you ever noticed what happens to the salt particles when they hit the hot frying pan? They just bounce around. They don't melt. They just stay a solid. It's really locked in that solid crystal lattice, and very difficult to even get any motion. The attraction so strong. So we're typically not looking at ionic compounds. Organic molecules, for the most part, that we're looking at boiling are going to be are going to be neutral compounds. And so what we're looking is for these dipole-dipole attractions between polar molecules. All right, let's take a look. Actually, I did skip one thing here. Is remember when we're thinking about a polar molecule, we do have to consider geometry to determine whether or not the molecule is polar. So let's think about CCl4, carbon tetrachloride. Carbon tetrachloride, what do you think the shape of that molecule is? That carbon, what hybridization does that central carbon have? If it has 4 chlorine atoms, 4 regions of electron density, we know that's going to be sp3 hybridized. So it'll be tetrahedral. So this is tetrahedral. How do we draw a tetrahedral shape? 109.5, a little wider than 90. We could draw 2 bonds in the plane. And then where are the other 2 chlorine atoms? One is going to be a wedge and one is going to be a dash. One is sticking out towards us and one is pointing behind. So that's our tetrahedral shape. Okay, now, yes, it has polar bonds, right? Chlorine is more electronegative than carbon. And so it will pull, each of these chlorine atoms is pulling away, but because it is a completely symmetrical molecule, every single one of those dipoles completely cancel. They all cancel. So it ends up being a non-polar molecule. So we talked about that actually on the very first lecture, looking at polar bonds, polar covalent bonds, and then polar molecules we said have to do with the geometry. Now we have the tools to be able to predict the geometry of the molecule based on the hybridization of the various atoms. So here's a case where we would see that actually this ends up being a non-polar molecule. So assuming the geometry gives us a dipole where we have one area that's partial negative and one area that's partial positive, that's when those molecules are going to be kind of sticking together like magnets. All right, dipole. Now let's take a look at hydrogen bonding. Hydrogen bonding is still just another example of a dipole-dipole attraction. It's a partial plus attracting to a partial minus, but it's the strongest known dipole-dipole there is because it's extremely partial positive and extremely partial negative. And when does that happen? That happens when we have either an NH bond or an OH bond, because these are, remember what we said about oxygen? What do you know about oxygen's electronegativity? It is the second most electronegative atom in the periodic table, right? So this is a huge, sorry, I need a pen. This is a huge polar inductive effect towards the oxygen, electronegative effect towards the oxygen. So it has a huge partial negative on that oxygen, huge partial positive on that hydrogen. The hydrogen atom is so tiny, it really can't put up a fight for those electrons. So the oxygen really just takes them all away. Okay, and the NH is also quite polar. So this is also a partial minus and a partial plus. So not as extreme as the OH, but NH is also a very, very strong dipole moment. So those extremely polar bonds can cause hydrogen bond formation. So when we look at something like water, water has nothing but OH bonds, right? So this is really, really good at forming hydrogen bonds. We have the partial negative oxygen. Sorry if that is covered up a little bit. This is a partial negative oxygen, partial positive hydrogens. So if you put this into water, I'm sorry, if you bring in another water molecule, you would expect that the partial minus oxygen is going to be strongly attracted to the partial positive hydrogen, so strongly attracted that we actually draw a dashed line connecting the two that we describe as a hydrogen bond. So a hydrogen bond is an attraction between two molecules of the partial positive hydrogen of one and an oxygen of the other. Okay, and this can continue in every direction. So every hydrogen is going to be attracted to the oxygen of another water molecule, and so on and so on and so on. It ends up being this huge network of interconnected water molecules, and that's what gives water its really unique properties. It has a very, very high boiling point. and it has a high surface tension, right? What happens if you put a droplet of water on, on a surface, it beads up, it makes a water droplet, and that's because water is attracting to itself. It really wants to be around other water molecules. Where else might we have some interesting impacts of hydrogen bonding? If you look at the DNA base pairs, the AC pairs or the GC pairs, right? We have AC with adenine and thymine, and I'm sorry, AT and GC. I need to review my biochemistry. Adenine, thymine, and guanine and cytosine are the base pairs that are on the two strands of DNA, and those two strands need to be held together, but not permanently, because what does DNA have to do? It has to separate in order to replicate itself, right? That's how the genetic code gets passed on to the next generation, is the strands separate, and it makes copies of each strand and so on. So that connection between the two strands has to be a temporary non-bonding interaction. And what it does is it does that by hydrogen bonding. So here's the structure of cytosine and guanine. And when you look at these, you see they're perfectly set up to do some hydrogen bonding. Okay, over here we have the NH bond, that we need to have an NH group to be what we describe as the hydrogen bond donor. The hydrogen bond donor that has the hydrogen that can be donated to the hydrogen bond, and somewhere we need something with a lone pair that's electron rich, that can serve as the hydrogen bond acceptor. So hydrogen bond acceptor. So in the case of water, water is both the hydrogen bond donor and the hydrogen bond acceptor, which makes that, all that cross-linking so strong. And in this case, we have two different groups, one of each. So there is our hydrogen bond between our donor and acceptor. And there's another hydrogen bond we can form. Do you see another option here? Here we have a nitrogen lone pair, and we have an NH. So this is, again, perfectly set up to do a second hydrogen bond. And in fact, there's a third hydrogen bond we can make between the GC base pair, between this last CO double bond. The oxygen group here can form a hydrogen bond with the NH, the third NH group. So they're just perfectly aligned. I actually have some models. I'll bring those out in the problem solving session. That the geometry is just beautifully set up for this these two to come together and be held very, very reliably, so reliably that we can pass down consistently the blueprint, from generation to generation. Okay, so what effect does it have on boiling points? Let's look at some data here. So let's look at these four compounds, very dramatically different boiling points. Water has a exceptionally high boiling point for such a small molecule. And again, that's because it has lots of hydrogen bonding, extensive hydrogen bonding, because all it has are these very, very polar OH groups. Okay. But then when we compare these next two, they both have oxygens, they both have polar bonds, right? They both are polar molecules, but what's the difference? Why is there such an extreme difference in their boiling points? Because this one has that OH group. This could be a hydrogen bond donor and hydrogen bond acceptor. So this one can form hydrogen bonds, and this one is no hydrogen bonding. They are isomers of each other. They both have the same number of carbons, oxygen, hydrogens, same size molecules, but one can form hydrogen bonds, super, super strong attraction between molecules, which makes it very, very difficult to pull them apart from each other. Okay, and now how about these last two then? These last two, can't do any hydrogen bonding again. But why is this one such a lower boiling point compared to this one even? Now we're comparing polar versus nonpolar. So this last one, this hydrocarbon, is completely nonpolar, where this one with the -24 temperature has no hydrogen bonding, but it's polar. So it does have some dipole attractions that can increase the boiling point. Not an awful lot, because look at our boiling points. They're both negative. Do you know what room temperature is in Celsius? We usually don't do much in Celsius, but room temperature is something like whoa, sorry, I can't spell tonight. Room temperature is something like 24 degrees or something like that, or 20 degrees, somewhere around there, depending on whether it's a hot day or a cool day, right? So somewhere on the order of 20 degrees is room temperature. So if these have negative temperatures that where they will boil, that means at room temperature they're what state? They're going to be gases. They're going to be a gas at room temperature. They're going to be gases at room temperature. So these are both gases. Where this one is a liquid, because now it's, you'd have to heat it far above room temperature in order to boil it. And of course, water, we know at room temperature is a liquid as well. All right. Let's look at an example here. How about these three compounds? If you want to pause the video for a second, see if you can predict which one do you think would have the lowest boiling point, which would have the highest boiling point. What do you think? Again, they're all roughly the same size molecule. We are going to talk about the effect of molecular weight on boiling point temperatures. They're roughly the same size, but what are some things you want to look for? The number one thing to look for is hydrogen bonding, because that's the strongest attraction we can have between molecules. So can any of these hydrogen bond? Can any of these hydrogen bond? There's the magic group that we want to find. If we have an OH or an NH, you must have that in order for hydrogen bonding to take place. Okay, so this one has, it can form hydrogen bonds, let's say that way, can form hydrogen bonds. So this we expect to have the highest. This should have the highest boiling point. The highest boiling point. Okay, and what about the other two? The other two, we have any, what kind of attraction do we expect? Next, we can look for polarity. Do we have any polarity between these two? This middle one is a nonpolar molecule, and this last one is a polar molecule. This has a polar bond. We expect that to be a polar molecule. So what would have the lowest boiling point? The lowest boiling point would be the one that is nonpolar. And the polar molecule that can't hydrogen bond, can't form hydrogen bonds, would be somewhere in between. And so this one is in the middle. And that is in fact the case. If we look up their boiling points, this is the same molecule here. This is called ethanol. Ethanol has a boiling point of 78 degrees. And this, the one with the double bond, compound number 2, has minus 48 degrees. And the middle one boils around room temperature, somewhere around there, 20 degrees. So what we can't do is predict what will the boiling point be, right? We have no way of coming up with a number, okay? But what we should be able to do is look at two compounds and decide the relative boiling points. Which one would you expect of the higher boiling point and the lower boiling point, and why? Can you explain that? You're going to see that on my exams. There's tons of and why questions, so you're going to have to be ready to explain the answer that you're proposing. Fantastic. All right, so finally, let's take a look at this nonpolar molecule. So why does this even have a boiling point of minus 48? Why is it not like a minus 100? Why would this ever be a liquid? Why would these two molecules of this this compound ever have any attraction to come together to be in a liquid state or even a solid state? Okay, there must be some attraction between molecules, even nonpolar molecules, that don't have, that don't act like magnets, that don't have these permanent dipoles that will hold them together. Okay, and so then this last effect is the weakest effect. That's why we're talking about it last. It's called van der Waals forces, or London dispersion forces. And these can be described as temporary dipoles. that molecules might experience, and if there's temporary dipoles, then there might be some temporary attraction between molecules. Okay, and these again are present between all molecules, but for nonpolars is the only thing that they have going for them. So what we can imagine is if we just have this kind of this big molecule, and we might imagine that there's just some, not exactly even distribution of electrons. Sometimes there's a little bit more here and a little bit less here. They, because electrons are moving. And so if this area right here is electron poor, just temporarily, right? This is temporary. Then that's going to induce a dipole in the next molecule to make this electron rich. So this is gonna now have a little bit of electrons are going to be drawn to that area to counteract the electron deficiency. So we end up having an attraction between molecules, temporary attraction due to uneven distribution of electrons. And what this really ends up being is a surface area effect. This is something that the bigger the molecule, the bigger the surface area, the more they're going to stick together. This is what the observation really is that molecules are just sticky. They're just sticky. They like to kind of stick to each other because they have electrons that might be shifting around. So the effect we have there is kind of like Velcro. Okay, so one thing that we're going to be looking for is that the higher the molecular weight, the larger the molecule, the more surface area it has, therefore the more London dispersion forces that it has. Okay, assuming everything else is equal. So if they have the same polarity, then a bigger molecule is going to have a higher boiling point. It's just going to be harder to tear it apart from the others and move it into the vapor phase. Okay, so let's take a look at a series of compounds. These are all hydrocarbons. These 4 compounds are all hydrocarbons. They all are just carbons and hydrogens. They're all nonpolar, right? But they have quite different boiling points. Okay, this one, here we have the smallest molecule. This one is only 4 carbons, right? This is 4 carbons. These are both 5 carbons. So these two have the exact same molecular weight. They are isomers of each other. Same exact molecular weight, same number of carbons and hydrogens. And then obviously we have one that's 31 carbons. So we have this huge, long, giant compound. So because it's so massive, there's just a huge attraction between molecules, and we have a huge boiling point, higher than 300 degrees. This is maybe the structure you would find for something like beeswax. So again, very high boiling point, even though it's totally nonpolar. So at some point, your van der Waals can actually overcome. It'd be more important than stronger than hydrogen bonding even. But that's why we're never going to be like comparing apples to oranges. So in this case, notice we're looking at all nonpolar compounds. So we're just have one thing at a time. Here it's molecular weight. So the one with the 4 carbons has the lowest molecular weight, has the lowest boiling point. And the one with the highest molecular weight has the highest boiling point. Okay, now how can we distinguish between these middle ones? These are isomers. They have the same molecular weight, the same mass, but they have a different shape, and therefore they have a different surface area. Okay, notice that this one is really branched, and so it's more spherical. It's more spherical. So if we look at these 2 compounds, this one has a shape that's more spherical, and this one has a shape that's more linear. So you can kind of think of this as more linear versus spherical. And what effect does that have on the surface area? The linear molecule has more surface area. Again, if you think of this like Velcro, right? A long Velcro strip is going to be very, very hard. If you bring 2 Velcro strips together, very hard for those 2 to separate. So more surface area means more contact and higher boiling point, which is exactly what we see, right? This has a boiling point of 36. This one has a lower boiling point of 10. because with the spherical shape, it has less surface area. Less surface area, meaning less contact. And therefore, it has a lower boiling point. Right? Think Velcro. You ever have the one of those like dart boards that's with Velcro, just little Velcro balls, you know, you throw them on the dartboard and they never even stick because there's such a small point of contact between the two that it's really hard for them to stay there. Okay, now it turns out we're only going to be looking at boiling points. When you look at melting points, things are a little different. Okay, so just FYI. So being spherical means it's easier for the liquid to turn into a gas, but this shape would have better crystal packing. Better crystal packing. It can pack more efficiently if it's spherically shaped, and so it has an increased melting point. Okay, we're not going to study melting points. We're not going to study melting points because it turns out that there's more than just these intermolecular attractions. The way that they pack also impacts the melting point. So we don't have the ability to predict relative melting points. So we're going to stick to boiling points instead. All right, and so here's our summary. Okay, the most important thing to look for, because the strongest attraction we can have is what? Hydrogen bonding. So first look to see if there's any OH or NH bonds that are present. If we have those, then we are capable of forming hydrogen bonds between molecules. Then we can look to see polar versus non-polar, because dipole attractions are very strong. Okay, and then we can look to see what the differences are in molecular weights. And finally, if all other things are equal, like we had here, both non-polar, both the same molecular weight, then we look at the shape of the molecule. So the branching is the very, very last thing, and that's assuming everything else is equal. Everything else is equal. All right, those are the boiling points. So last but not least, let's talk about water solubility, or any solubility really. Solubility has to do with the concept of like dissolves like. Oh, I'm sorry, I should mention, don't forget skill builders 9 and 10. Skill builders 9 and 10 have to do with predicting boiling point trends. And so in section 14, we talk about water solubility. The theme here is like dissolves like. So the way one species is going to dissolve, a solute is going to dissolve in a solvent, is if they have similar polarities. So what do we know about water? We know that water is very, very polar, and it can form hydrogen bonds. It can undergo hydrogen bonding. So if what we're trying to dissolve in water also is polar, or maybe also can form hydrogen bonds, that's going to be very good interactions and therefore a high water solubility. So let's take a look at these three compounds. We have all of these they're called alcohols. FYI, we'll be learning about that name down the road. When a carbon chain has an OH group on it, we call it an alcohol. And what we're doing is we're varying the length of the carbon chain of that compound. So what do you think about a carbon chain? Is a carbon chain something that you describe as polar or non-polar? Polar or non-polar? This portion of the molecule, I would say, is very non-polar, because again, what do we know about carbon-carbon bonds? Totally non-polar. Carbon-hydrogen bonds are non-polar as well. So these are non-polar. Is that something water would be attracted to? Not so much. It's kind of the opposite of water, right? So in fact, I would call this part of the molecule hydrophobic. Hydrophobic. This part of the molecule doesn't like water at all. You could even kind of describe it as greasy. Hydrocarbon chains are greasy. They're oily. So this is something that would not have a good interaction with water. So this is actually the one that is the least soluble. And as we shorten the carbon chain, when we get to the one to the far left with 2, this one is the most soluble, because we have this very polar OH group, and a very small nonpolar region. And then the 3 carbon one is somewhere in the middle. This is going to be less soluble, and the last one's going to be least soluble. So if we look at the data, this one with how many carbons are here? 1, 2, 3, 4, 5, 6. So this 6 carbon compound, you could dissolve less than 1 gram for every 100 milliliters of water. So a very, very small amount will dissolve. The middle one, you could dissolve about 8 grams of this for every 100 milliliters of water. And the one with just 2 carbons, we describe as miscible. Miscible means it's soluble in all proportions. Soluble in all proportions. So this is called ethanol. Ethanol is a liquid, so you could start pouring ethanol into water and it will dissolve, and you can never pour in too much ethanol that it will separate out into 2 layers. It's always going to be soluble. Where this one with 3 carbons, this is called propanol. Propanol is also a liquid. You could start adding a few drops in and it'll dissolve, and a few more drops it'll dissolve, and then eventually it'll get saturated. It'll have the maximum amount dissolved, and then all of a sudden you're going to see a separate layer of the propanol with the water. So no further amount will dissolve. But miscible means you can never add too much and have it you can never add too much and not have it dissolve. Okay, so let's look at another example here. This last compound is called acetone. Acetone is organic liquid we use a lot in the lab to help wash glassware. You might use that. It's a solvent, organic solvent. If you use nail polish remover, sometimes the nail polish remover is acetone based. And this is another molecule where it's miscible with water. When you're using a nail polish remover, it's usually an acetone water mixture. And why is it so favorable? Why is it so much like water that it will dissolve so readily in water? Well, because it is very polar. We have this CO bond, so we have a partial minus, partial plus. So even though it doesn't have an OH group, it has a very, very polar region and very small non-polar regions to counteract that. And it is also a hydrogen bond acceptor. So how could this interact with water? It can actually accept a hydrogen bond from water and interact that way. So not only does it have dipole attractions, but it can have hydrogen bonding as well. So acetone is a highly soluble organic molecule, but we'll find that most organic molecules to be water soluble have to either have very, very small carbon chains or have to have lots and lots and lots of very polar groups like OH groups. Okay, so we should be able to predict relative boiling points and relative water solubility based on the intermolecular attractions that we talked about today. Okay, so believe it or not, we have finished up, or finally, we finished up chapter 1. Again, all over the place. You'll find on this last page a review of all the topics that we covered in the order that I covered it in this lecture, which was a little bit out of order sometimes with the book, but we did a review of general chemistry concepts. We talked about how to do line drawings and Lewis structures, and these skill builders will help you get some practice in those areas. We talked about atomic orbitals and hybrid orbitals, and leading to 3D sketches. And then finally, we did molecular polarity and physical properties. I kind of moved isomerism up a little bit to an earlier lecture. But I've listed here the different skill builders. Those are really good in-chapter problems to work on. And then once you're done with working on all those skill builders and other in-chapter problems, then you can move to the end of chapter problems. Those are nice because they kind of mix them all in together. And that's a little bit more like what you would find in an exam situation where, hey, here's a random organic chemistry question. Can you answer it? So that's a good place to go. Have some a little extra data here for some boiling point data. Again, just to remind you that that the first thing to look for is the molecular weight. The molecular weight. And the branching only when you have two isomers. So because these are both 4-carbon isomers, that's when we're going to look at the branching to explain the difference in boiling points. But even though this is branched and this is not, because this has 5 carbons and this has 3 carbons, we notice a huge difference in boiling points just based on the size of the molecule. Don't look at the shape unless everything else is equal. So there we have it, our first chapter in organic chemistry. The lectures are done. We have some problem solving sessions to work on together, and lots of extra time spent working on textbook problems. All right, that wraps it up for now. I will see you again soon. Take care.